You're in the ICU and there's a patient you're quite worried about. You come to the bedside. The patient's saturation on the monitor is 92%. But then the nurse hands you a blood gas and the PaO2, the arterial oxygen tension, is substantially lower than you would expect. You are horrified. Is this an anomaly? Is there something wrong with the lab result? Is there something wrong with the pulse oximeter? Or is this a function of normal physiology? This tutorial looks at the Oxyhemoglobin Dissociation Curve. Fundamentals of anesthesiology and critical care. With me, your host, Pat Nelligan. Understanding gases and vapors. This tutorial is on a key topic in physiology, and it's about the Oxyhemoglobin Dissociation Curve. In the previous tutorial, I discussed oxygen content and delivery, what is hemoglobin, how hemoglobin carries oxygen, how you calculate out the oxygen content, oxygen delivery and uptake, and what happens with blood loss. In this tutorial, we're going to narrow things down a bit and look at what happens when oxygen binds to hemoglobin, why the Oxyhemoglobin Dissociation Curve is important, why it moves to the right and why it moves to the left. I'll explain the Bohr Effect and what 2,3-BPG or DPG, as you might know it, is. This is an illustration of the alveolar capillary interface in the lung. The airspace is at the top and the capillary lumen is at the bottom. The oxygen tension in the alveolus is 13.3 kilopascals or 100 millimeters of mercury. Blood returning from the right side of the heart has a pVO2 of 5.3 kilopascals or 40 millimeters of mercury. This is also the intracellular PO2 of erythrocytes or red blood cells. As gas flows from the alveoli into the plasma, the partial pressure of oxygen increases to 12 kilopascals or 90 millimeters of mercury. The gas immediately diffuses from the plasma into the red blood cells, so the PO2 in the erythrocyte equalizes that of plasma. Remember, the erythrocyte started with a PO2 of 5.3 or 40 millimeters of mercury. The intracellular PO2 is lower than the extracellular PO2, and that's why oxygen rapidly diffuses in to bind to deoxyhemoglobin. Importantly, when that hemoglobin is fully saturated with oxygen, it becomes locked down and it rigidly holds onto oxygen until it has been transported to the tissues. This is sometimes known as the or relaxed state. The way I want you to look at hemoglobin is that it acts like a truck that securely carries oxygen through the arterial system all the way to the extremities and viscera. It then unloads the oxygen in the capillaries and then goes back to the lungs to pick up more. Absolutely core to this are the partial pressure gradients. Let's look a little bit closer at what is going on in the microcirculation. Oxygen is transferred to the capillaries through relatively impermeable arteries in the presence of a high PaO2. At this time, it is completely locked down so that the oxygen isn't released. Once red cells enter the microcirculation, hemoglobin is unlocked and it releases oxygen to the tissues. There is a sequence of events here. The blood enters the microcirculation and immediately the oxygen in the capillaries starts to diffuse into the interstitium, which has a significantly lower PO2. As the plasma PO2 falls, oxygen starts to diffuse out of the red blood cells and into the plasma and subsequently into the interstitium. There is a problem with this. The gradient between the capillary plasma and the interstitium is very high, and gases will always diffuse rapidly from high pressure to low pressure. As a consequence, oxygen will diffuse very rapidly along this concentration gradient if it was immediately released from hemoglobin, such that there will be maldistribution of oxygen delivery into the interstitium along the course of the capillary, all other things being equal. This is not something that we want. What we want is for the oxygen to be released gently, bit by bit, so that the oxygen delivered to the beginning of the capillary is the same as the oxygen being delivered to the end of the capillary. And this is achieved by a genius quirk of hemoglobin. It's differential handling of oxygen at different PO2 levels. And that is described by the Oxyhemoglobin Dissociation Curve, a core knowledge component in all of physiology. This is the Oxyhemoglobin Dissociation Curve. On the x-axis is the PaO2, the partial pressure of dissolved oxygen in plasma and within the red blood cell, and on the y-axis is oxyhemoglobin saturation. You will note that the curve is sigmoid. At high PaO2 levels, the saturation is very high, and at this level, oxygen is locked to hemoglobin. When the plasma PO2 falls to a specific level, usually around 8 kilopascals or 60 millimeters of mercury, or a saturation of about 90%, the lock opens and the curve rapidly descends downwards. This corresponds to the point where hemoglobin starts to dump oxygen. These are the normal numbers for the oxyhemoglobin dissociation curve. Note that this is the point where the curve becomes steep, and this is the saturation and content of mixed venous blood as measured in the pulmonary artery. We can now map those numbers onto the curve. At 99% saturation, the PaO2 is 12 kilopascals, 90 millimeters of mercury. Going down the curve, at 90% saturation, the PaO2 is 8 kilopascals, 60 millimeters of mercury, and that is where the steep part starts. At 75% saturation, the PO2 is 5.3 kilopascals, or 40 millimeters of mercury. That's the mixed venous point. And finally, at 50% saturation, the PO2 is about 3 kilopascals, or 23 millimeters of mercury. Let's dig deep into the curve. So we start with arterial blood leaving the aorta, where the PaO2 is 12 kilopascals or 90 millimeters of mercury, with an oxyhemoglobin saturation of 99%. At the end of the microcirculation in the veins, that oxygen has depleted with a PVO2 of 5.3, 40 millimeters of mercury, and a mixed venous oxygen saturation of 75%. Looking at the flat upper part of the curve in more detail, you can see that at relatively high oxygen tensions, oxygen is tightly bound to hemoglobin until a critical point is reached. You can see nothing much changes until we hit about 8 kilopascals. At this point, 90% saturation, the saturation per unit oxygen drops off quite considerably until we get to that mixed venous point of 5.3 kilopascals, 40 millimeters of mercury. At about 8 kilopascals or 60 millimeters of mercury, hemoglobin goes from that locked-in, relaxed state to the tight state where oxygen is ejected, part of which is driven by carbon dioxide, as we'll see later. This keeps the distribution even within the microcirculation. Hypoxemia moves the patient onto the steepest part of the curve. In this situation, the oxygen leaving the lungs has a PaO2 of 8 kilopascals, that's 60 millimeters of mercury, and a saturation of just 90%. It is on the steepest part of the oxyhemoglobin dissociation curve. As a consequence, all other things being equal, once the red cell reaches the arterial capillaries, oxygen is rapidly dumped into the tissues. And once the PaO2 reaches the same tension as the interstitium, then the diffusion of oxygen stops, even if the end of the capillary has not been reached. The mixed venous oxygen content falls dramatically, and cellular hypoxia will ensue. In addition to the curve being steeper as the capillary PO2 falls, there is another element that impacts its dissociation, and this is the Bohr effect. The Bohr effect was described in this paper in 1904 by the Danish physiologist Christian Bohr. And it describes the curve shifting rightwards as the PCO2 increases. Let me explain this. Hemoglobin can exist in two states: a tense state where it unlocks, pushes oxygen out, and is less amenable to oxygen binding, and a relaxed state where oxygen binding is encouraged. The tense state exists in the tissues and the relaxed state is in the lungs. Sometimes it's difficult to get your head around this concept of tense versus relaxed, so I'm going to give you an analogy that will make this easier to remember. Imagine if you're lying in a hammock on a tropical island, the sun is shining, everything is good, you're really relaxed, you're being snugly held by the hammock, and all is good. And that is what is happening to hemoglobin when it's going through arterial blood. It's very, very relaxed. It's just holding on to oxygen. There's no problem. The oxygen sits there very happily. But as the blood flows from the artery into the microcirculation, that hammock starts to tense up, so it becomes much more taut or tight or tense. And simultaneously, that area becomes somewhat hostile, and the PaO2 drops and the partial pressure of CO2 rises, and that hammock is getting tighter and tighter. And this is what happens in the tense state. The hammock tightens and ejects the oxygen from hemoglobin, and the hemoglobin is dropped into the tissues. So now in the tissues we have hemoglobin in the tense state, and then as it travels back towards the heart in the venous side of the circulation, it relaxes again to welcome more oxygen. While oxygen is loaded in the lungs and unloaded in the tissues, carbon dioxide is continuously produced by mitochondria, and it diffuses very easily into the interstitium, into the plasma, and into the red blood cell. Within the red blood cell, carbon dioxide can bind directly to hemoglobin, and this is known as carbaminohemoglobin. Alternatively, it can be hydrated with water catalyzed by carbonic anhydrase to form carbonic acid. Now, this rapidly dissociates to release a hydrogen ion equivalent and bicarbonate. The hydrogen ion binds to hemoglobin, and the combination of carbon dioxide and hydrogen ion binding to hemoglobin changes the state from relaxed to tense, increasing the release of oxygen into the tissues. This is the Bohr effect. So returning to our truck analogy, carbon dioxide nudges hemoglobin to dump oxygen, and the more carbon dioxide present, the more oxygen is released. And once carbon dioxide leaves hemoglobin in the lungs, hemoglobin develops a higher affinity for oxygen. Rather than going up and down the oxyhemoglobin dissociation curve, what's happened here is that it has shifted to the right. In the lungs, carbon dioxide is exhaled, lowering its partial pressure. That results in an increase in the pH. The environment is less acidic and more alkaline, and hemoglobin affinity for oxygen increases, shifting the curve to the left, promoting oxygen loading. Hemoglobin becomes relaxed. And this is an example of the curve shifting to the left. So what does it mean when the dissociation curve moves rightwards or leftwards? For example, normally at a saturation of 75%, the PaO2 is 5.3 kilopascals or 40 millimeters of mercury. If the curve shifts rightwards, what is the likely PaO2? Is it 5.3 or 40 millimeters of mercury, 6.6 or 60 millimeters of mercury, or 4 kilopascals or 30 millimeters of mercury? The answer is number 2. With a rightward shift, there is lower saturation for the same PaO2. There are a range of different metabolic conditions that will cause shifts of the oxyhemoglobin dissociation curve. For example, the curve is going to shift rightwards if there is an increase in the demand for oxygen. When does that occur? It occurs in states of hypoxemia, such as ARDS, where there is an increased production of lactate or carbon dioxide, so there's increased acidity, where the temperature goes up, and in a specific situation where there is increased 2,3-BPG or DPG within red cells. I'll explain that in a minute. The mnemonic for changes to the right is cadet. C-A-D-E-T. C for increased carbon dioxide. A for increased acid or reduced pH. D for increased 2,3-DPG, which is more correctly known as BPG. E for increased exercise or increased cardiac output, situations such as sepsis. And T for increased temperature. So at 90% saturation, the PaO2 will be higher than you would expect, 10 kilopascals or 75 millimeters of mercury. At 75% saturation, the PaO2 will be 6.6 kilopascals or 50 millimeters of mercury. And at 50% saturation, the PaO2 will be 4.4 kilopascals or 33 millimeters of mercury. Conversely, what happens when the oxyhemoglobin dissociation curve shifts leftwards? In this situation, there is a higher saturation for the same PaO2. In other words, hemoglobin is in the relaxed state, and that happens when there is less metabolic activity going on. So there is reduced acidity or alkalinity, reduced temperature, reduced PaCO2, and reduced 2,3-BPG. In this setting, the numbers can be a bit of a surprise because the PaO2 is much lower than you would expect for the level of hemoglobin saturation, particularly if detected by a pulse oximeter. For example, at 90% saturation, the PaO2 may be 6 kilopascals or 45 millimeters of mercury. At 75% saturation, the PaO2 may be 4 kilopascals or 30 millimeters of mercury, and at 50% saturation, the PaO2 may be 2.7 kilopascals or 20 millimeters of mercury. Just to give you the full flavor of the shifts, these are color-coded. Blue is the normal oxyhemoglobin dissociation curve. Green is the rightward shift, red the leftward shift. And we're going to look specifically at 75% saturation. Normally, at 75%, the PaO2 is 5.3 kilopascals or 40 millimeters of mercury. When there is a rightward shift, the PaO2 is higher than you would expect. It's 6.6 kilopascals or 50 millimeters of mercury. If there is a leftward shift, the PaO2 is lower than you would expect. It's, in this situation, 4 kilopascals or 30 millimeters of mercury. Rightward shift, increase offloading. Leftward shift, increased affinity. Now let's move on to a mysterious substance that has been known to generations of students, doctors, and scientists as 2,3-DPG, but it's more correctly known as 2,3-BPG, and that is 2,3-bisphosphoglycerate. It is a metabolite that's a byproduct of glycolysis. The concentration within the red blood cells is 2 to 5 millimoles per liter. That is not insignificant, but there really is none of this stuff in plasma. It's continuously produced by the red blood cell, but the more metabolic activity, the more 2,3-BPG that is produced. It nudges hemoglobin into the tense state, so it shifts the curve to the right and increases oxygen offloading. This is the metabolic pathway of 2,3-BPG. Glucose enters the red blood cell and is converted to glucose 6-phosphate and then to 1,3-bisphosphoglycerate. Some of this is diverted and converted to 2,3-BPG. This is the Rappaport-Lubring shunt. It binds reversibly to hemoglobin when oxygen tensions are low. It is released after the oxygen tension rises, for example, in the lungs, and is converted back to 3-phosphoglycerate that is subsequently converted to pyruvate and lactate. As there are no mitochondria in the red blood cell, the lactate is pumped out and shuttled to lactate-consuming tissues as a major form of energy. This is oxygenated hemoglobin, and when red cells arrive in the tissues, they are holding on to oxygen avidly, and that release doesn't happen until the PaO2 falls below a critical level. But in situations of hypermetabolic activity, there is an increase in the amount of 2,3-BPG within the red cell. That causes a conformational change, loosening hemoglobin's grip on oxygen, dumping oxygen into the tissues and shifting the oxyhemoglobin dissociation curve to the right. Now, most of you are familiar with this product. This is red cell concentrate. When you give blood, you give whole blood and it's separated into its component parts, and the red cells are concentrated and suspended in a small amount of plasma. These cells are still metabolically active. They're alive, but they're cooled down and stored for several weeks. The production of 2,3-BPG is reduced by cold storage, and due to metabolic activity, after about 3 weeks, there is no 2,3-BPG left, and there is a leftward shift in the oxyhemoglobin dissociation curve of this stored blood. As a consequence, transfused blood delivers less oxygen to the tissues than fresh blood. It takes 2 or 3 days for this blood to deliver oxygen as effectively as one's own blood. Red blood cells, as I have mentioned, have no mitochondria. As a consequence, they are entirely dependent on glucose for energy and glycolysis as their main metabolic pathway. As a result of this, red blood cells produce enormous amounts of lactate per day, somewhere in the region of 320 millimoles or 29 grams, but maybe a lot more. And this production increases exponentially in stress states as cardiac output and oxygen delivery increases. The acid associated with lactate reduces the pH of blood and plasma and shifts the oxyhemoglobin dissociation curve rightwards, independent of 2,3-BPG. Now, let's review this tutorial. In this tutorial, we looked at the oxyhemoglobin dissociation curve and why it's important, why it has an S shape, why it moves to the right and to the left. I discussed the Bohr effect and finished with a discussion of 2,3-BPG. I hope you found it useful, and I'll see you soon.